Now that we have generated a volcano on a wire-stack plot, we can move on to fitting the spectrograms displayed in the wire-stack graph using the third module. Before doing that, let's make sure that the concentration range and bin size returns a reasonable number of spectrograms to fit. Click on the Tools button to view the concentration information. As you can see here, the concentration range is from 0 to 800 with a bin size of 20, which would result in 40 spectrograms. I'm going to increase the bin size to 80 so that only 10 spectrograms are generated over the whole concentration range. Since we have made a change to the concentration bin size, we should check that the wire-stack plot still looks reasonable. Since the wire-stack looks good, we can also look at the volcano graph. This graph is visibly smoother since we changed bin size. Now that we have satisfactory parameters, we can move on to the third module where we can fit the spectrograms created. To open the module, click on the third module button. The module fitting window should appear on screen. Based on the concentration range and bin size chosen, you will see a different number of spectrograms under the plot. Since we had a bin size of 80 with a maximum concentration of 800, we have 10 spectrograms to fit. The first and lowest concentration spectrogram is labeled number 1. As we click through the spectrograms using the green arrow keys, we can view higher concentration spectrograms. We confirm that by looking at the wire-stack graph alongside the model fitting panel. You should be able to tell that the shape of the spectrograms match the wire-stack graphs. Before we start fitting, let's look at the settings being used in this module by clicking the Settings button. In the first box, you should be able to adjust how many Gaussians are being used to fit the spectrograms. For instance, you can remove all Gaussians except 1 and 2. If we apply the setting and look at the model fitting panel, you should be able to see that we're only fitting using 2 Gaussians at this point. The first Gaussian has a median at the effective monomeric brightness, which is set to 72. The second Gaussian has its median at double the effective monomeric brightness, so it's at 144. The second Gaussian represents where a dimer would appear. If you want to include higher order oligomers, you can open the settings window back up and add 4 for tetramers and 6 for hexamers. It should also be noted that the 2 checkboxes in this window, when checked, allow the effective monomeric brightness and the standard deviation to be freely adjusted by the Autofit tool that is available in this module. These checkboxes are generally only checked when the user is using the Autofit feature when analyzing monomeric construct data. So if the effective monomeric brightness is not determined yet, and the user is determining it from the monomeric construct data, then these checkboxes may need to be checked so the effective monomeric brightness and the standard deviation can be adjusted to determine those values. Since we have already determined the effective monomeric brightness for our fluorescent protein, we can use those values. We'll be using 72 for our effective monomeric brightness and a value of 35 for the standard deviation. Remember, we will not be checking the boxes that allow the effective monomeric brightness or the standard deviation to change when the Autofit feature is being used. By leaving the boxes unchecked, those previously determined values will remain fixed. In order to do a manual fitting, you can adjust the amplitude of each Gaussian curve using the slider above the 2 blue arrows. The text at the top of the slider tells the user which Gaussian is being adjusted with the slider bar. To adjust Gaussian 1's amplitude, drag the slider bar down. To move to other Gaussians, click on the blue arrow buttons and then drag the Gaussian's amplitude down. You can see that the axes scale with the Gaussian amplitudes, which help us visualize the data easily. You can manually continue to refine the fit. However, we also have an automatic fit button that adjusts the parameters for us and minimizes the residual. To use this feature, click on the green play button at the top of the panel. You can see when I click the button, it snaps the curves to the data. With subsequent clicks, it adjusts each Gaussian amplitude to minimize the residual. Now that this spectrogram is fit, we can move on to the next spectrogram by clicking the green arrow key to move on to the next graph. To fit this spectrogram, we are simply going to use the Autofit feature. You should be able to see that on the first click, the graph snapped to the data but adjusted itself with subsequent clicks. Specifically, a small hump showed up near the middle of the graph after multiple clicks. Now we're going to go through the rest of the spectrograms and fit them using the Autofit feature. Confirm that all spectrograms are fit to your satisfaction by navigating the spectrograms using the green arrow buttons. Once all spectrograms are fit, we can extract species fraction information by creating a kinetic curve. Click on the Plot Model button to generate the kinetic curve plot. The kinetic curve shows a species fraction information versus concentration graph. Bear in mind that each spectrogram has a different concentration range. My concentrations are centered on bin sizes of 80. The first point is at 0, the second at 80, third at 160, and so on. You can see that I have 10 points because I fit 10 spectrograms. From each spectrogram fit, the species fraction information is derived from the amplitudes of the Gaussians. In this specific data, we can see that the monomer, which is denoted by the red curve, is dominant at low concentrations. You should be able to see that when we look at higher concentrations, the higher order oligomers start showing up. The kinetic curves generated are great comparison tools when determining if the addition of a ligand influences oligomerization. Once the kinetic curves have been generated, the species fraction data can be saved in an Excel format. A snapshot of the graph can also be saved with the snapshot tool.